let's put our capillary on here. And I'm going to do it like this. And then at some point, right, I'm going to switch over to. So this is a capillary. This is the arterial end of a capillary here. And this is the venual end of the capillary here. Okay, so you're okay with my structure? Now tell me, and the direction of flow in here is this way, right? Tell me what happens to the hydrostatic blood pressure as we move through here. Does it stay constant? It decreases. It has to, right? The further we are away from the heart, this has to drop. So let's just show this dropping as we pass through here. Okay. All right with that? We could put some values on it. How about if I say this is about 40 millimeters of mercury here. And this is about, I'm trying to make my math work here, 40. Time. These numbers don't matter. The absolute value of these numbers doesn't matter, because guess what? Would these absolute values change depending upon where you are in the body? Yes, because the further away you are from the heart, they're what? Lower, obviously. But they're proportionally, the idea is still the same, that it drops. That kind of makes sense? So the numbers can change, doesn't really matter. I just put some on there just for fun. And then inside here, not only do we have this hydrostatic blood pressure, and this is a pressure that's favoring, which direction does this want to move things? Out of the capillary from plasma to interstitial, or from interstitial to plasma?
Interstitial to plasma.
Is it a force pushing against the wall? Against the wall of the blood vessel from inside, or is it pushing against the wall of the blood vessel from outside? From inside, it's pushing out, right? That's blood pressure, right? If you got a hose, and you've got water in the hose, that's the blood pressure. Right? And you stick holes, punch a bunch of holes in the hose, what's going to happen? Stuff's going to come out. So now answer the question. Is this pushing out or pulling in?
Pushing out.
Pushing out, right? So it's a positive pressure pushing out. So it's a positive pressure. You okay if I say it's a positive pressure? I mean pushing out. It's just stronger here than it is down there. Okay. Now what about pie? Like pumpkin pie. What about pi? The osmotic pressure is pulling in, and since the proteins don't come out, it stays relatively constant throughout the entire length of the vessel, right? Does that make sense? Because in order for it to change, we'd have to have these proteins moving across the membrane, and they don't. So it stays relatively constant. So there's pi. And I'll give you a number. And again, actually this number's kind of high, but put it in there. I'm going to say it's 30. So it's 30 there, and it's 30 here. Now this pressure, is it a pressure pushing out or pulling in? Pulling in, because it's a higher osmolarity, right, than the interstitial fluid, so it's pulling in. So are you okay if we call that a negative pressure? You okay with that? Because it pulls in. Is that okay?
Yes.
All right.
Do we have a choice?
So the net pressure is a function of these two, right? So at the arterial end, blood pressure is greater than osmotic pressure. Yeah? So the net, is it a positive pushing out or a negative pulling in? positive pushing out, right? Do you believe me? And can we give it a value? About 10 millimeters of mercury. So 40 minus 30. Out, right? What about over here? So now we're at the denule end. Negative 23, negative 30, it's plus 23, negative 30, so it's a negative pulling in, right?